centralized and decentralized systems are not the same. That's not a surprise, definitely. And decentralized systems behave very, very differently from centralized applications. The guarantees that the decentralized systems have, the failure modes, the scaling properties, and all of those things emerge, right, from the interaction across many independent components, rather than being controlled by a single service. If we talk about centralized applications, usually the architecture is linear. You have these requests that comes in, the service processes the requests, and the results comes out, right? If something breaks, and if you do an analysis, usually this analysis leads to either one component or one specific path, or you can usually identify things. Because at the end of the day, like, the environment is completely under your control, right? It is true that traffic patterns may fluctuate, but definitely the topologies doesn't. And the state of the things lives in one place, which is the central server, right? Of course, there can be some sort of replication if it exists, but usually this is engineered around the well-known patterns. Now, when we think about testing in a centralized environment, usually the mental model tends to be also straightforward. The system, because the system is built around a single authoritative service or cluster, clients talk to the same backend. The state lives in a controlled database. The traffic flows through predictable entry points, and so on and so forth. 1 second. Sorry. Okay, so from an engineering perspective, this means that we can often isolate performance issues. Like we do a profiling of the server, we can do a profiling of one specific route, we can do a profiling of a database query, or we can basically just scale we can check the scaling dimension, right? The system's behavior is primarily dictated by how efficiently the central component performs the work. And to scale, we basically either scale up the service or we scale out to replication patterns, right? That we also have control. So when we test these centralized systems, it's mostly about ensuring that the service holds up under increasing load, that the latency remains acceptable, and the resources scale proportionally. And also, even in failure modes, the failure modes follow familiar patterns, right? If the database slows down, everything slows down. If the API fails, the whole system fails. And I think the good summary is that because the architecture is kind of hierarchical, right? Most of the problems are also hierarchical. And I mean, most importantly, these systems remain stable as long as the central authority remains healthy and responsive, right? And this predictability is what makes centralized scalability evaluations relatively direct and contained. Well, in decentralized systems, on the other hand, these are emergent systems, right? There is not a single node that holds the global truth. There is not a single operator that controls the network conditions, latency, packet drop, message propagation, consensus synchronization. These are like ingredients that define how the system behaves. And this means that the correctness doesn't come solely from writing correct code, but also it comes from observing how the correctness degrades, right? How it recovers and how it stabilizes across the network of interacting peers. There is no primary server, right? It's not like a primary server that performs the best, dominates the rest of the nodes. Each node usually acts as a consumer, as a contributor. And I think this is very important to have in mind, because the behavior we care about is not limited to our node, right? The behavior that we care about is related to how all nodes interact and what global behavior emerge from these interactions. So I think, in other words, we must change this perspective of individualist approach to a part of a self-organized system. And also this means that if we want to scale, it's not just throwing CPU and memory at the machine, right? It's about understanding the phenomena of how message amplification works, the propagation of delays, peer churn, or bandwidth asymmetries, or whatever, right? It's about how the shape of the network itself changes under load, and how those changes in topology also can influence the performance. I'm sorry. When we talk about testing decentralized systems, we are not talking about checking that the given function returns the right value or not. Like, this is, I would say, this is a completely separated leg. We are talking about creating and evaluating realistic conditions, right? We want membership churn, adversarial environments as well, message load. We may want to resource constraints the resources, and this helps us to reveal the true character of the system, right? It is about to discover how small implementation differences can become large systemic effects. It's how this surfacing behavior, a single developer, you cannot encounter that in isolation, right? What I want to say with this is that you can increase the number of peers in a decentralized system, and you can study if it increases the traffic linearly or not, right? But there is more than that. And later I have a small example. This increasing of peers can result in changing the propagation path. It can alter gossiping dynamics. It can trigger peer rotations, which is the example that I would mention. It can shift which nodes are becoming a bottleneck, and so on. So a small variation in one node can create a cascade effect, and that can affect all of the nodes, all of the other nodes. And again, like, it's hard to replicate these behaviors in a single node test, right? You can't. And I mean, obviously, unit tests and integration tests are extremely important and useful. But as I mentioned, like, we are looking at different things, and I think that's also important to take into account. Okay. What else? Yeah. Of course, like, decentralized systems, they require shared ownership, right? There is not a single person or a single team that controls the full life cycle of the data. They cannot control the message dissemination. If something goes wrong, you don't have this nice, good-looking trace error in the terminal, right? It gives you symptoms, and these symptoms are dispersed across logs. They are dispersed across metrics and the states of the nodes. So it's not like you can check a node, or you can check one machine and say, yeah, I understand the health of the whole system. Like, you cannot do that. Everything is distributed. The resource usage is distributed. The bandwidth consumption is distributed, of course. So to evaluate the network, you need, like, systemic metrics. Like, you need a distribution of propagation. You need a histogram of latencies between nodes. You need network cohesion under churn, right? It's these are the characteristics that emerge from the system. And again, like you cannot check this on the like with isolated components, right? And another thing that that it's a major difference is that in decentralized systems, like they introduce eventual or like a probabilistic correctness, right? It's not like you have a strict immediate consistency. Like this means that we have to observe not just what happens in an ideal settings, but how the network converge under adverse conditions. How fast a node can recover from message lost, how robust membership information comes when the environment is noisy, right? Also, how does the network, like how does the system behave when a node is temporarily disagreeing, right? Usually in a centralized system, disagreement is a bug. In decentralized systems, like this is the normal thing, like nodes disagree, and what matters is how reliable the network resolves this disagreement and goes back into a normal global state. And also there is another thing, it's we also have the adversarial dimension, right? And this is something that decentralized systems rarely face because the adversarial approach is different, I would say. In a single misbehaving node in a centralized architecture is usually irrelevant. Like you are a malicious node and you are trying to affect, I don't know, Facebook servers, right? It's not like your intentions can do anything unless you can hack into the server, of course. But as an actor, as an external actor, you cannot do anything apart from DDoS and stuff like that. But yeah, in decentralized networks, if you have an unresponsive, unpredictable, or malicious participant, like this can affect the whole thing. This can slow the propagation, skew the routing, and basically it can degrade the overall performance. So then when we also do testing, we don't want to include the happy path and the ideal scenarios, but we want to stress the system, right? We want unreliable peers, we want high churn and latencies, partial failures, and also it's not like these are corner cases, right? They are everyday situations and realities in this kind of environments. So yeah, like this is another layer of difficulty to the already complex topic of decentralized systems. Okay, sorry. So after all this talking, I created this oversimplified example. We have two networks here. I created the network with Python and NetworkX, a nice library for graphs. And I created a random graph with an initial state that has 10 nodes. And yeah, I specified the condition that every node needs to have between 2 and 4 edges, right? And this is the initial state of the network. And then I added in the right example, I added a new node 10, which is here, that is not present here, right? What's the issue with node 10? Node 10, I will force it to connect to nodes that have 4 connections, like 2 and 1. And because we have this mandatory thing of no more than 4 edges, the nodes needs to reconnect, right? And basically this creates a cascade effect, as I mentioned before. And this results in a decently different topology, right? We can already see the connections between 9089 and things like that, but also there is another thing, and it is like the path between node 1 and 8 in the first example is 1. And because we added a new node, which is 10, the path from 1 and 8 now is 3, right? It's hard to see because 8 and 4 are connected. This is not a connection to 2. This is 8 and 4. And also 9 and 7. This is another line. 2 is not involved here. So if we want to go from 1 to 8, we need to do 1 to 2, 2 to 5, and 5 to 8, right? Or 1 to 7, 7 to 4, and 4 to 8. And so basically with just one node, we have a path of a difference of path of 3 jumps, just because of that. And I think this is a nice example because it can also help us thinking about important topics such as connection management, right? How do we handle connection management? Obviously, when we are doing this decentralized software, we need to decide at some point, like, what's the number of maximum connections? And then what happens if we reach that number, right? Do we allow newer connections and then we drop the oldest one? Do we reject new connections? And depending of those decisions, also we are affecting security, right? But also we need to find a balance between having new peers and not accepting every new peer, right? And yeah, the other topic is that are we talking about the same implementation? What happens is because we are assuming these nodes are the exactly same software, right? What happens if 10 is a different implementation? How is defined the number of maximum connections? Is this defined in the RFC, or is this defined in, where is this defined? How this needs to be explicitly documented and defined, right? Basically, I'm trying to just illustrate like how a small implementation difference can have a larger effect on the system. Yes, and this is the other thing. Yes, I will. Then connecting to the previous point, I think one of the core things that we also have to take into consideration when we are building these systems is observability. Yeah, there is the topic of security as well, but because in synthetic scenarios, in experiments like the ones we do in DST, like this is extremely beneficial because you can add as many information as you want, and then when you like are ready and you finish testing things, like you get rid of this information if you want, right? So basically, it's nice to have this added observability or added information during the development or testing phase. Yes. So what I mean by this, right? Imagine we are node 10. We join to the network, and this is the final state of the network. We, as node 10, we have absolutely no idea that the connections between nodes 9, 0, and 8 changed. Like, we don't know. Do we know about the length of the path between 1 and 8? We don't know. Do we care? I mean, as users, we don't care. As a developers, if this is causing a problem in the network, then we do care. Can we know that it happens? Yes, if we have full observability of the network, and this is the important thing. In controlled scenarios, we are allowed to do this. Once we don't do that and we just deploy the software and everyone runs their own thing in his own house, we don't have access to this. So deploying in production is useful, yes, but if you don't control every node, like, can you assert that, for example, a message that you published was received by every node? Like, you don't have access to the whole information of the network, right? And good luck trying to debug an issue like that if you don't have access to the information. Sorry. Another thing is that how we can assert this, because these behaviors, the behavior of our implementations, this needs to be asserted. Like, you don't suppose it works, because then you are doing random things, I guess. So let's take this example. We are working with a friend request functionality, right? You can obviously you will do this integration test where you will create one node, and this node will send one request, and then you have another node, and this node will receive one request. Okay, good. Is that enough to check if everything works? I don't think so. I think there are many other things that need to be checked. Are there nodes in the middle of this request? Because this request may need to be forwarded. Do the nodes have different modes? Like, is one node a light node and the other a full relay node? Is the path between the request a mix of those nodes? Are they from different implementations? So imagine we have 10 nodes, a bunch of nodes, and every of those nodes will send 3 requests to 3 other nodes. And we have this information in the logs, right? Friend request received. Can we assert that the functionality is correct? I mean, you can think, okay, if we have 10 nodes and every node is receiving 3 requests, then we have 30 requests, and that's it. Okay, is this a good indicator? Yes, it is a good indicator. Are we asserting functionality here? No, we are not. Like, we cannot assert the correct functionality. We cannot assert the delays. Like, I'll calculate the delays, for example. For that, we need some kind of timestamp, right? Then we add the timestamp to the thing. Can we check delays after that? No. We still need to know when the send request was sent, right? Then you can say, okay, we can check to the sender. We can check the sender node logs to see if we have something like a send friend request. But still, you cannot correlate the two requests, right? You can think, okay, if sender is logging send friend request at time X, and then the receiver is friend request received time X plus 1 millisecond, you assume this is the same request because the difference in time is extremely close. But again, that you are assuming things, you are not asserting things. And then what happens if the same node send 2 requests, right? Like, you don't have access to analyze this information. And this is why you need to improve as much as you can the information that you're providing. If you are receiving a friend request, this needs to have an ID in order to correlate with the sender. It needs to have a sender timestamp, because this is also important. It's not the same that when you are receiving it. You have to know also the peer ID. So once you have this information, you have to think, can I fully trace the behavior of this functionality? And if the answer is yes, then it's good to go. If the answer is no, then we are missing something. Like, we need to stop thinking about, again, individual behavior and how the whole thing affects the information and how we can assert this information. Yes, RFC documentation, right? Good old friends, technical documentation and RFCs. I mean, I will not do this analogy of engineers that are trying to build a bridge from 2 different parts, and they need to meet in the middle, and the bridge need to, but basically, as a introduction, RFCs are basically the blueprints of everything. And they define exactly how the technology should behave, right? How the data is sent, how the security works, how the systems talk to each other. And thanks to these softwares built by different companies in different countries at different times can still work together. And And pretty much what I said now in this whole talk connect directly to this. Then also we have the technical documentation. This is important inside organizations, largely because code changes. People might leave, new people might join. The system can evolve, and usually a good documentation explain why decisions were made. It's not just about what was built, right? And this prevents things like repeating mistakes or wasting months rediscovering knowledge that was already there, which is a common situation. And I mean, I can understand the feeling, right? At the end of the day, you need to finish the task as a developer. This means that, for example, your code needs to compile, needs to work, and adding documentation will not make the code compile, right? Then you leave it at the end, and then you have to do another task, and then you don't do the documentation, and remains there, silent. Then you, for some reason, there was a specific behavior that was not captured in RFC, or you had to decide certain thing in the code, and you do it. You don't document that. It's like a very specific thing, and then a person 2 months later faces that encounters that behavior. It's not documented anywhere, and you spend hours or days or weeks trying to check what's going on just to find out that it's working correctly, and you just wasted weeks, right? So there is this balance between how much time can I spend today writing code that can save days later. And another important thing that I almost forgot is that regarding RFCs is that they allow doing theoretical studies before even starting a single line of code. And if we are talking about distributed systems, this means that we can reason about the system behavior under failure, under latency. We can check outages in advance, right? So by formalizing assumptions and protocols early, this helps to uncover like hidden complexities. You can validate architectural decisions, and I think this is crucial because also it significantly reduces the implementation risk, right? And then on top of all of this, then you can get these results and validate those experimentally, right? Experiments you can do experiments, and you can compare the results with the real ones, and then assuming everything will work. And in short, like this, between RFCs and technical documentation, like they enable scale, interoperability, security. Very nice thing to follow those two things and do. Okay. Complex challenge, and you have to start from RFC to code and documentation, testing, integration tests, and then you are still not sure, right? Luckily, we have a team precisely dedicated to this. We have resources to this. We have the capabilities thanks to the machines and the tools that we are developing to do like to be like the first entry point of the software, right? I mean, I am not saying that it's impossible to achieve, but so far I didn't see a single piece of decentralized software that worked first try, right? It's not common. Maybe it happened, but I am not aware. So at least with the DST team, we have an extra sanity check, right? And if it doesn't work, then we collaborate and then we fix the issues. And in order to do this, I think there are questions that needs to be answered before even contacting the team, right? You need to, as a developer of whatever project you are building, you need to think about what you want to do you want to deliver this to the final user in its current state? Like, is it ready? If, for example, you think we can start playing with whatever implementation, do we need all the necessary information, or there are things that needs to be clarified, right? Because if not, then the starting point is not good. If you plan to test the functionality, do you know what you're looking for, right? Because we can help with this, but you have to remember that as a separated unit, project maybe was developed during years and years of work and meetings, and we may have a decent lack of context there, right? So it's not like, hey, we finished this, now we use it. It's like you have to have ideas about what you expect, right? You expect an estimate amount of resources. You expect more or less these latencies, right? You expect this to work in this specific way. At the end of the day, you are building this because you want to solve a specific problem, right? And so you have to know how you are solving that problem, and then we assert this solution, right? And then together we can work on what other things can be checked. But the first approach, like the first important things that needs to be checked, this of course needs to come from the primary developer, right? And also, instead of, if we are not talking about testing, if we are talking about doing a change, a new protocol, an improvement, or whatever, also I guess you will need assumptions, right? We did this change to the protocol, so we expect less latency, for example, right? And these kind of things. So I mean, basically, to sum up, like, communication is a crucial component. I want to mention that from our side, collaboration with other projects, if the question starts with "can you do?", the answer from DST will be yes, because at the end of the day, if we're talking about code, I mean, unless you are asking for impossible things, it can be done, right? We just need to talk about the scope and the resources that we have. But if we are talking about deploying testnet that you have full control over it, and then do X experiments with, I don't know, chaos engineering, with measuring whatever thing you want to measure, cross implementation, testnets, whatever, this weekend, right? And what else? Oh yeah, that I think this is beneficial to everyone and important, because you cannot assert those things once you don't have control over the software, right? So luckily, we have the people and we have the machines for doing this, and sorry, we can assert either capabilities or functionalities of the software. So yeah, hopefully with this, hopefully the structure was decent, but I wanted to like remind that what we are building is very different from standard software, right? And because we have this extra complexity, we also need to do extra steps in order to test or assert the functionalities of the things that we are building. And yeah, I think this is everything, at least in the presentation side. I don't know if you have questions, and if not, maybe we can discuss about the topic. Thank you.
Thank you, Alberto. I think it's very explorative presentation. I thought that we can just pass the code to the DST team and you are going to test it thoroughly and get back with the report or something. But we need to have some good communication and expectations about the what we produce. So yes, Arunima, there's a question? Yeah.
No, I was just about to send the clapping emoji and by mistake I clicked on the hand. Sorry.
Okay. Yes. Another question or ideas? Yes, Corey.
If there's no questions, I'm happy to like either go through some more context on kind of the historical evolution of software testing that then led to the need for things like everything Alberto just described, or clarify anything that he said in terms of distributed systems testing or decentralized systems testing, which is slightly different.
Okay, let me close this so I can see.
Yeah.
Any specific thing you wanted to mention? Because I mean, the topic is,
it's huge, but like I like people giving people like we and Alberto were discussing before this and previously, and I wanted kind of the end goal for this discussion and or anything that stems from this discussion to be all of the developers and engineers, software techs, protocol engineers, et cetera, that work here, that work on things, building decentralized systems, as they're building, to have the kind of like correct mindset in how things can break as they're building. And you can kind of do that by understanding a little bit about decentralized systems testing. Because you're building software for a single node, but the context of the network is where you need to be thinking about. And so how an individual node impacts the network is usually the types of things where you should be asking about how to break it. And so when you come to the distributed systems testing team, you're looking for that type of validation on, we think the network scales this way. We've done theoretical testing that shows, say, it scales exponentially with the number of users for some given dimension, maybe like messages for gossip network, things like this. Can you verify that? Here's the implementation. And the tools that distributed systems testing has available to them enables them to do reasonably rigorous, realistic simulations to then experimentally show that, yes, as you increase the number of nodes in the network, this part does scale exponentially. So like you've implemented correctly, or you understand that portion of it correctly. And you really can't know that until you do the testing in reasonably realistic scenarios.
I think the issue is that unless you do it, maybe it's not easy to see what can happen, right? So it's also a matter of, how can I say this? Experiment it yourself, right? And because you don't have access in your standard CI thing, right? When you are writing the software, unless you are not doing it. And it's not, I think what I want to say is that it's not something that the people usually think about when write software, right? Yep. Because the paradigm is much different. And if you are used to write standard single node software things, you don't, I think it's weird that you stop and you think, okay, how this piece of code that I am writing right now can affect the whole network, right? Because it's something that's not easy to think about. And I think the benefit of also doing these experiments and doing these tests is to show how important it is, and maybe it helps to, when you are writing code, to be aware of these things, which I think it's not easy.
Yeah, it's also worth mentioning that even if you do understand the concept of decentralized systems testing, it's very difficult to have access to the resources that allow you to do the actual experiment. So for instance, like you can run a number of nodes on your own machine. So like but I was sent this over to Alberto, I think it was yesterday, this progression of testing software like this. And one is like, I test a single node. And there's a number, I can go through a gamut of ways in which you can test a single node. But then if I want to test the network aspect of this thing, I can run a bunch of them on one machine. That gives me some type of view that they're communicating with each other in an ideal way, with like the ideal interface between them, connection. But I'm limited in that kind of realistic actual network topology. So the next thing I can do is maybe have a couple machines on my LAN or network that I own. I can run it on machines and test it that way, but then you need orchestration software. And as you scale out the number of nodes and the required resources to simulate real networks, the resources required to do it grow quite quickly.
Yeah.
And the tooling required to keep the level of observability intact, and then subsequent analysis of all of the logs and stuff like this, and something gets more and more and more difficult. And that's the skill set that the distributed systems team has built up over time. Is not only the resources, but also the required tooling and the understanding of how to do the aggregation of everything, and then subsequent analysis to see how this stuff actually works. It's like, how would you end up doing, say, a network partition on your own computer? That's not necessarily straightforward or easy or realistic.
And not only that, because when you are thinking about that, maybe you are also forgetting how the network stack works in the operating system, right? Because maybe you are trying to do something like that. You use Docker Compose, you spin up 20 containers, whatever, and everything looks that it works. And this is a real example. I mean, this happens with Quick in Nimble peer-to-peer. Locally in Docker Compose, everything was perfect, right? Everything worked, the communication was good, and that's it. Once you are using different machines, just different machines, we are talking about 20 nodes, 50 nodes, something like that, the thing was failing. And with nothing else in the middle, right? So just how also the operative system handles the communication between nodes internally in the same machine is different to when you are using multiple machines, right? And this also can help to discover things that are wrong that you don't know because you are just using a single machine. That's another example, yes.
I made a visual that if people are interested, I can share on the progression of I guess I call them testing areas. I was doing some I'll call it vibe writing of the history of testing with Claude the other day, and then when I finished, I wanted to make a number of diagrams, and so this is the kind of culmination of that. I'll share it here, blow it up. So if you look at like the story that I created, I can share this later if people actually care, want to see it, was like if you look at the history of computing architecture, how it changed forced additional changes in how we test software within that architecture. And it started with sequential systems, namely like single computer, single machine, single user, and trusted, right? Those are kind of I don't know, like 4 dimensions of things you need to care about when looking at software and the architecture it runs on. And so one of the breaking points of this era was the fact that as you moved into multiple cores on a single machine, you had thread interleaving issues, so that the types of testing you were doing, which was unit tests, I forgot what TD is, but certain like things you would normally do when you think about testing, don't work when you're working in a threaded environment. And then they moved into concurrent systems and the software that runs on those. And so as you move from this gap to the next one, so this introduces kind of new failure modes that the new testings has to take account, right? And then when you move beyond single machine to multi-machines, you then end up with network partitions and partial failures across machines, and how that then breaks the current software methodologies, which is a distributed context. So a distributed context is software that runs on multiple multi-threaded machines, but under a single, we'll say, administration ownership. So it's trusted. And so your new failure modes you have to end up working with are network partitions, partial failures, split brain, message log. There's a bunch of things you need to account for that previous testing methodology never got to. And so this orange box and everything beyond it is the domain of distributed systems testing. We've just taken it all the way to adversarial testing, which we'll get to in a moment. And that's where things like chaos engineering, partition injection, these types of stuff started coming into play. Jepsen started really taking a hold here and becoming the standard of how you test these types of systems. And so if you go look at the Jepsen tests, that's still like the canonical standard for, is this good software or is this a good protocol or architecture? And then multi-tenant systems happened, and that's where like containerization happened. So you have multiple softwares on multiple machines, but each of those machines also has different types of software running on them. So you have different type of shared resource view, right? And then finally, like this is still trusted in a way in which you have centralized administration of these things. And so you're still have a tremendous amount of observability here, if not total observability here, meaning that the admins can see everything. And then because they can see everything, they can diagnose problems much quicker. The moment you move into peer-to-peer systems and adversarial settings where like you don't have control over who runs the software, and so the network is this mixture of individuals with their own intentions, it becomes kind of the worst case scenario. And the way in which you test for those things are the most difficult to handle, namely because you need to ensure that the software is 100% committed to the contracts that it's supposed to be doing, namely like the software does exactly what it's supposed to do and nothing else. And then all of the associated network conditions. And so like, does the consensus protocol work under what conditions? And it becomes the hardest thing to do. And so even the fact that we have a team like this in the organization is something that almost no one in the ecosystem has. And I don't think we take enough advantage of it. But I thought this was an interesting way to tell the story of like how historically we moved to the decentralized system we have today. And as you've moved from distributed systems testing to decentralized systems testing, it's become the most hardest thing we've done in terms of computing. And so testing to make sure the stuff works appropriately is also kind of the hardest. And it's still, I'd say, in its infancy. So that's all. And yeah, tools. This has some other stuff too. This show like what type of tools we have available to us to look for these types of things over time.
Thanks. Yeah, I agree, especially on the last part.
Yeah, there's so many tools. Like this doesn't exist. Some of the things we have, like Kurtosis, Shadow, the in-house tools we've built. Some of the visualization stuff Wings used to do was phenomenal.
And I think also it represents how hard it is to check how many different approaches were tried to be built for doing these decentralized tests, right? Because I think I found 3 or 4 frameworks that were planned to do decentralized testing, and all of them were abandoned by one reason or another, especially because difficulties and things like that. And I think most of them were relying on single machine scaling, which is, yeah,
not going to get you very far.
Exactly. And the others, I think it was related to Docker Swarm and things that were not
didn't scale well.
Yeah, exactly. Yeah.
Like when we tried to hit was it 10,000 nodes for status? That was Probably some of the largest realistic simulations that I've seen done before, and all the frameworks that we tried up to then just broke because, like, down to like Docker limitations, right?
Even recently, I think a couple of months ago, I saw an article from Google, I think it was, where they did large deployment in Kubernetes for AI training, and I think they were talking about 160,000 machines or something like that. It was very interesting, right? Because now that the AI at some point will move to also decentralized computing, because yeah, it is what it is, right? So I think they will also push for that, and it will be interesting.
Yeah. So I feel like this will get eventually moved into a forum post on VAC. So like, I urge people that if they have questions or comments on this type of stuff to ask them. I'm happy to share any of the things that I have if they find it interesting. But like, we should really be thankful and take advantage of the fact that we have a team here and resources regularly allocated to trying to make sure that the software we build does what we think it does before we end up deploying it and finding out that it doesn't. Like the nature of decentralized software is that once you deploy it, if you do it appropriately, you no longer control it. And so like, you're kind of stuck with the contracts you deploy. And if they're broken, then fixing them is a much more difficult process than doing the appropriate amount of investigation and due diligence beforehand and fixing them before you deploy it.
Yeah.
Alexander?
So this, thank you, Alberto. First, it's very interesting talk. And my question is related to Corey, this kind of evolution which you showed, like, yeah, how it went kind of from the sequential and to the distributed systems. So I don't know, is any parallel here basically in physics where you went like from one molecule, right, understanding what it does, you know, like that's a sequential case, like one computer to then to those networks of computers, right? Like your case of distributed systems, adversarial, whatever. I mean, it's a more like a system with many molecules which interact, right? Kind of like that. Yeah.
Yeah. I tend to think about this evolution of things to the kind of, I would say, budding science of complex systems and emergence, and which has led to, over the past, I'd say, especially 10 years, a tremendous amount of implication on all of the sciences. But agent-based modeling came from the discovery or the development of complex system analysis. And with the physics appropriate version of this is like how temperature is a emergent phenomenon from bulk molecules.
Yeah, that's what I was kind of trying to understand.
The decentralized systems are by definition complex systems. And so I'm seeing a lot of the formality of that science being applicable here. I'm kind of curious. I've been following it, but I'm curious to see how some of the stuff they do could be used for with a more theoretical analysis side of things. Like how to construct protocols that give you the type of emergent phenomenon you want, and then how to test for it.
Yeah, it seems to be like you know, when we are kind of going from single molecule to many ones, right? We need to kind of look at things differently, right? Then we need to, I mean, as you said, like for example, temperature, it's like a bulk properties. We need to kind of to look at them, and then probably like the system, how well it performs, it's going to be based on those kind of like measurements, like of a bulk.
Yeah. So like temperature of a molecule is a meaningless concept, right? It requires a bunch of molecules in order to discover what a temperature is, because temperature is an emergent property of a group of things. The same can be said about decentralized network on a network. So like I'd say like the stability of a network is not something you would put towards any individual node, but every individual node contributes to the stability of the network. It's a bulk property.
Okay, yeah, thank you.
Maybe adding on to that, if I'm thinking about it, like as you've moved from distributed to multi-tenant to adversarial, you're increasing the degrees of freedom of an individual node within the network, which makes things even more complex, right? So it becomes even more harder to come up with or to pre-construct the desired emergent phenomenon on what you want them, like how do you want this network to behave? Given all of these degrees of freedom, how do you make something that results in that behavior when you don't control everything in the network? It's a really difficult, if not impossible, thing to do. But like the goal of decentralized systems testing and all of the stuff is to get as much confidence as possible, so that you have some level of, you know, hope that it works the way you want it to.
I think we all convinced about the hardship of the testing the complex, maybe the complex adaptive systems. But we can, as a developers or the RFC creators, can be more insightful to have DSD team about the testing with the better current expectations, or I don't know, better communications, right?
Yeah. That's all I got. I can talk about this for days, so unless someone has some questions, I don't want to waste everyone's time.
I mean, just because I was thinking, right, how useful it is, because when you were saying that it's very hard to control, to define the emergent behavior from the nodes, right? I think it's more beneficial to be strict with the freedom that you provide to the node, right? Because the more freedom you provide to the behavior of a node, the less control you have over the, like, the more this node can affect the global network, right? So in terms of the restrictions from an RFC point, I guess, it's better to have everything as defined and strict as possible. I think is, I don't know, I was just thinking about that.
Yeah, it's hard though, right? Because like what we're trying to build is permissionless systems, meaning that people can kind of predict what they want, and the only track that really matters is what is valid and invalid. And like looking at the context of and Nakamoto consensus, Satoshi's vision was single core, single vote. Didn't even have the understand the concept of mining pools and ASICs and creating Nakamoto consensus. Here we are. So sometimes it's so incredibly difficult things because you don't even know how the hardware and architecture will change over the next 5 to 10 years. And the only thing they really have is on action to change. Really hard to constrain everything. Like specifications are in the contracts on what's valid and what's not. When you look at like the kind of must and shall, like shall and shall not wording of a specification, which is the definition of how different things agree, like if different implementations agree on things. Okay, cool. So those are your rules of the network. But then you have loose rules, like say for like the number of connections as your management. You can't really enforce those things as we can, like and consensus. And because they're built up of complex operate and your ability to control because it's even more complicated.
Yeah.
The effects for the honest, and we should
always it makes it all so much worse.
So, if there's a man malicious, there's no rules for that. But I think this is not the case of so much part of your DST, right? So of course, the decentralized system should be secure against some attacks, but in general.
Maybe for another call, another, I guess, something that we're doing that may or may not be making it more difficult for us to do this is making privacy more fundamental in the base layer, like it's lower in the stack. And there's this fundamental trade-off of the ability to optimize with how private something is. And so, like, if you view privacy as a lack of information, the system becomes more generic, and the tubes in which you're passing information through become more dumb. And because of that, the ability for the people in the middle that are routing messages, because they can't see into the messages in which they're routing, lack the ability to optimize. And so there's this kind of fundamental trade-off of the ability to optimize with the increase in privacy. And I'm really curious to see how that comes into play. Like how performant can we make these systems when we're optimizing for so much privacy, which then reduces our ability to make decisions as message passers to make things simple for ourselves.
But I think
or even do the testing, right?
This is also related to the security, right? I mean, because it's hard to optimize, but also it's more secure, or should be more secure, right?
It's a multi-dimensional problem.
Yeah.
It may be more secure in one way, but less in another way, because it's so easy to spam a node and kick it off the network.
Yeah. That's
they
right.
can't handle spam.
That's right. Yeah.
Is it kind of the era 6, the privacy malicious networks? Privacy preserving malicious networks.
Anyway, something to chew on.
Any other ideas, questions?
That's it from my part.
I don't see anything. There's no comments on the YouTube channel for the stream, so we can wrap it up.
Okay, so just to repeat the query, don't worry if you missed this live session. To ask a question, just visit vac.form.vec, which, yes, Corey, sorry.
I did the same thing that
Okay.
I even did.
So thanks to Alberto and Corey and moderators for this question. The next slot of IFT research call will be the next week on topic that anonymity in decentralized file sharing, practical limitations and open questions by Mohammed from local storage team. So yeah,